All right, so next, let's talk about collective communication in MPI. So again, collective communication are these routines where you can do communication between groups of processes. So there's several types of collective communication. The first one is one-to-many. Okay, so here you have one process which is communicating with many other processes. So one example would be a broadcast. Okay, so you have one process that sends a message to a bunch of other processes, right? And there's something similar to this which is called scatter. Okay, so we'll talk about all of these in detail later. There's also many-to-one. Okay, so instead of broadcasting a message, right, maybe you could have a process get messages from all of the other processes. Okay, so that's many-to-one. And then you can also have many-to-many communication, where basically all of the processes talk to each other. Okay, so one way that you can implement collective communication is, of course, you can just do a bunch of point-to-point communications. Okay, so for example, if you want to do a broadcast, right, then you can simply have the broadcasting process just send messages to every other process. Okay, but this is this is not efficient, right? Because that single process would have to do a lot of work. Okay, there's actually much more efficient ways of doing these collective communications instead of just doing individual point-to-point routines. Okay, right. I should mention that these collectives they are always blocking operations in MPI versions 1 and 2. Okay, but in MPI 3 they've managed to implement non-blocking collective operations. Okay, so now let's talk about the different types of collective communication primitives. Okay, so just as with the point-to-point communication, we need to specify the communicator or the group of processes that we're communicating with. Okay, now we're going to look at, so these are the different collective communication primitives we're going to look at. Okay, so the first one is broadcast. So in order to describe these different operations, it's good that we use this sort of visual representation. Okay, so if we look on the right over here, what we have is, so here I've drawn a grid, and what we have is, suppose you have P processes. Okay, so there are P rows in this grid, and there are also P columns. Okay, so the rows represent different processes, and the column represents data from different processes. Okay, so the way to think about a broadcast operation is that suppose one process, let's say the first process, has a piece of data. Okay, then if you do a broadcast, then the result of that is that all of the other processes will have that same piece of data. Okay, now that's the broadcast. The next operation we're going to look at is called, let's see. Okay, so they have the reduce over here. I think I'll talk about the reduce and the all reduce and scan operations later. Okay, so right now I'm just going to go with this visual aid, and I'll talk about the functions that are available in this diagram. Okay, so next, the next function to look at is the scatter operation. Okay, so here the scatter operation is something similar to a broadcast. Okay, but the difference is that here, so the similarity is that, again, you have one process, right? Let's say P0 over here, and that process is sending data to all of the other processes. Okay, but the difference is that for scatter, this process has a different piece of data for every other process. Okay, so if we have 6 processes, then this first process has 6 different pieces of data that it wants to send to the 5 other processes. Okay, and if you look at broadcast, so here we're sending the same piece of data to all of the other processes. Okay, so that's the difference between scatter and broadcast. Now the gather operation, okay, this is exactly the opposite of scatter. So here what happens is that all of the processes, they start with their own piece of data, okay? And you want to collect or gather all of this data at some particular process, let's say P0, Okay, so all of these 6 processes, they each start with their own piece of data. And then if you do a gather, then you end up with P0 having all of these 6 pieces of data by itself. Okay, now you can also do something called an all gather. Okay, so here all gather is just basically every process is going to do a gather. Okay, so the way to see this is that, again, we start out with each process having a piece of data like this. Okay, now if you do a gather on process 0, right, then process 0 is going to end up with all these 6 pieces of data. Okay, but for the all gather, actually every process is going to do a gather. Okay, so every process is going to end up with these 6 pieces of data. Okay, right, okay, and the next thing to talk about is this all-to-all operation. Okay, so all-to-all operation is basically, it's something like every process wants to do a scatter. Okay, so imagine that, so here you have a process, right? If this process does a scatter, then what's going to happen is that these different pieces of A data are going to end up on the different processes, right? Now imagine that at the same time, P1 also wants to do a scatter. Then what's going to happen is that all of these B pieces of data are going to end up on these different processes, right? And so for the all-to-all, right, we have every process is doing a scatter, essentially. Okay, so then we end up with each process, so if you have m processes, then each process is going to collect m pieces of data, okay, one from each other process. Okay, right, so these are the operations that we have. All right, so now I'm going to talk about these operations in some more detail and see how we actually use them in MPI. Okay, so the first operation is the broadcast operation. So the way we use this is that we have to say what data we're trying to broadcast. Okay, so then we're going to give a buffer, which is going to contain the data that we want to broadcast, right? And all of the data in this buffer has to have the same type, okay, which is this MPI data type here. And then we have count copies of this data. So for example, if I want to broadcast a vector with 10 values, right, then let's say 10 floating point values, right, then my buffer is going to have those 10 floating point values. Here my type is going to be MPI float, and my count is going to be 10. Okay. And then my communicator is the group that I'm going to broadcast to. Okay. And lastly, the source is which process is doing the broadcast. Okay. Now, okay, now remember that MPI is this SPMD model. Okay, so that means that every program, every process runs the same program. Okay, so here we're trying to do a broadcast from a source node, right? So let's say that node is node 0. Okay, so then node 0 is going to call this line in its program, right? But because every process is running the same program, then all of the other processes will also be calling MPI broadcast. Okay, so now what's going to happen is, okay, so let's do this with an example. Okay, so here the example is that let's say that we have a root node, which is node 0. Okay, the node with rank 0. Okay, and yeah, and the root node wants to broadcast a value of 1 to all of the other processes. Okay, so then this is our code for doing that. Okay, so we're going to call this MPI broadcast over here with this value of 1, right? And the source of the broadcast is going to be the root node, 0. Okay, but since we're in the SPMD model, all of the other processes, including the non-root processes, they're also going to be executing the exact same code. Okay, so all of the other processes are also going to execute this line over here, MPI broadcast, with the root being 0. Okay, so now that might look kind of weird, right? Because for broadcast, there's this asymmetry between the processes, right? You have one process which is sending the messages to the other processes, and everybody else should be receiving. Okay. However, when you run this in the SPMD model, it seems like everybody is broadcasting, right? Because everybody runs this line, runs this command over here, okay? So the way this is actually working is that since we're calling MPI broadcast with this particular root, okay, then in our case the root is 0, right? Then if my rank is actually, let's say my rank is actually equal to something like 2, okay, then when I call this MPI broadcast, my rank over here is because my rank is 2. When I call this function, I am not the root, and so therefore I'm actually going to do a receive. Okay, so even though all the processes are calling the same function, they do different things depending on whether they're the root or not. If they're the root, right, then when they call this MPI broadcast, they're actually going to do the broadcast. Okay, but if they're not the root, right, if my rank is 2, for example, right, then when I call this MPI broadcast, this is actually going to cause me to receive a value from the root. Okay, yeah, so just keep that in mind. It does look a bit strange the first time that you see it, but just remember that many of these collective operations, okay, not just broadcast, but many of them have this property that the data is coming from a particular process. Okay, and when you call this collective operation, then if you're the sending process, you actually do the send. But if you're any other process, then when you call that collective operation, you actually receive data. Yeah, so let's see. Yeah, so this just sort of says what I was explaining. All of the other processes, okay, including non-root processes, they're also going to call the MPI broadcast, okay? But because the rank is not equal to the root, then instead of sending, they're going to receive. Okay, so another way to think of this is that the MPI broadcast is actually saying, I will participate in a broadcast, okay? And then what I do when I participate depends on my rank, right? If I'm the root, then when I participate, I'm going to send. And if I'm not the root, then when I participate, I'm going to receive. Okay, and again, many collective operations work like this. Okay, they do different things depending on your rank. Okay, so next we have this operation called reduce. Okay, so basically reduce, let's just go with this example over here. So reduce, what's going to happen is that suppose every process has some data. Okay, so every process in my communicator starts out with, in this example, they have an array over here. Okay, so what I want to do with reduce is to basically collect all this data at a single node. And when I collect this data, I can choose to process the data in different ways. Okay, so here, maybe I want to sum all the data. Okay, so every process has a vector, and when I call this MPI reduce with the sum function, then I'm going to add up the values from all of the different processes, okay, in their vectors. So for example, when I call this MPI sum reduce here, right, the first value I get is 18, and 18 is equal to this 5 plus the 2 plus the 7 plus the 4. Okay, so this is what gets me the 18, right? So let's just check that, right? 5 plus 2 is 7, right? 7 plus 7 plus 4 is 18, okay? Yeah, and then the second value here, which is 14, right? So this is coming from summing up all of the second values in the vectors that the processes have. Okay, so you do 1 plus 3 plus 8, what is this? 12 plus 2 is 14. Okay, yeah, so this reduce is taking data from all of the other processes and processing this data and collecting this data in some way. Okay, so in this example, we're going to sum up all of the data. But in fact, we can do different operations on the data. Okay, so for example, we can maybe multiply the data instead of summing them. Okay, if we wanted to multiply the data, then what we would get is the first component would be 5 times 2, which is 10, 70. I guess we would have a 280 over here if we did a product. Okay, product. Okay, and the other one is going to be whatever it is. Okay, I guess 48. Okay, and there's some other operations that you can do. For example, you can do the max or the min. Okay, now if you do the max, then what you're doing is you're going to produce two numbers. The first number is the max of the first entry in all of these vectors. Okay, so it's going to be the max of 5 and 2 and 7 and 4, so it'll be 7. Okay, so if we did max over here, right, the first entry is going to be 7, and the other entry is going to be the max of 1, 3, 8, and 2, and so the second entry would be 8. Okay, if you did min, right, then I guess you would be getting something like, what do we have? We would be getting 2, right? That's the first min, and 2 and 1, okay, if you did min. Okay, so that is the reduce operation, right? We're going to take values from all of the other processes and then combine them. And if the other processes have a vector of values, then we're going to also produce a vector of values. Okay, so the signature for this function is basically yeah. So we're going to have a send buffer and a receive buffer, and a count and a data type. Okay, so the count and the data type is just what kind of values are we sending here? So here they're going to be integer values, and then the count is going to be 2 because each process is sending 2 values. Okay, and the operation, this is going to be one of these either min or max or sum or product or other types of operations. Okay, now here the target is which process is receiving all of these values. Right, because we're reducing all of these values onto some particular process. Okay, so here the target is going to be process 0, right? And the send buffer, so every process which is not the target, okay, well, actually it also includes the target, but every process is going to have a buffer, and it's going to have a send buffer, and the data for the reduce is coming from all of these different send buffers. Okay, so these things over here, right, they're the send buffers at the different processes. Each process is gonna have a send buffer. Okay, and then the reduce buffer is only the target node needs to have a reduce buffer. Okay, because only he's gonna collect all of this data. Okay, now I want to mention that again, all of the processes are going to call this reduce function. Okay, both so in this reduce. Process 0, of course, calls the reduce function to collect all of this data. Okay, but the other processes 1, 2, and 3 are also calling the reduce function. Okay, but the difference is in how they behave. So in process 0, when because he's the target, then he's actually going to collect a bunch of data from the other processes and then add them up. Okay, the other non-target processes, when they do the reduce, they're just going to send their value to the target process. Okay, so this is just like the broadcast, where everybody does the same function, but the actual procedure you go through depends on whether you're the target or not. Oh, right, and yeah, so I just want to mention that, so one of these functions is not so obvious. So this MPI max location, okay, so this LOC stands for location. So this is actually going to return a pair of values, and the pair is, so this is basically doing a max of all the values, okay? But it's going to tell you where the max came from. So for example, if we do a max loc over here, right, then the first value, the first max value is going to be 7, and this is coming from process 3, right? So sorry, let's write this a bit nicer over here. So this is going to say, sorry, the 7, 2, okay? It's going to say that the max value in the first coordinate is a 7, and process 2 has this value of 7. Okay, and then for the second coordinate, right, we would have 8, 2, okay, because the max in the second coordinate is going to be 8, and it's again going to come from process 2. Okay, so that's the reduce function where we reduce onto one particular target process. The all reduce function is very similar, except for we're going to reduce these values onto every process. Okay, so therefore you don't need to have a target, you don't need to specify a target process anymore, right? You just need to specify what is the data you're sending, right? And every process needs to now allocate a receive buffer to take all this data from. Okay, so now if you compare this picture with the previous picture, right, they're the exact same thing, except for in the previous, for reduce, right, only process 0 received these sum values, whereas for the all reduce, all of the processes receive these sum values. Okay, so the next operation is called scan. Okay, so scan, again, let me just show you an example of what it does. Okay, so scan, every process begins with a value or a vector of values. Okay, and then what happens is that, well, these processes have ranks, right? So we're going to order the processes according to their rank, right? And now the ith process is going to get, okay, well, there are different types of scan operations, but let's say that we're doing the MPI sum scan, okay? So if we're doing the sum scan, then the process with rank I is going to get the sum of the first I values, okay? So for example, this process over here, right, if you're doing MPI sum, then he's going to get the sum of the first value, which is just 1, okay? The second process is actually going to get the sum of the first 2 values. Okay, so 1 plus 2 is 3, right? The third process gets the sum of the first 3 values, so that's 6. And then the fourth process sums all of these values, so he gets a 10. Okay, so this operation is called scan. Okay, and again, you don't have to use sum here. You could use something like, let's say you can use product. Okay, so prod, right? In that case, the first process would get 1, right? The second process would get the product of the first 2 values, so that's 2, right? The third process would get the product of the first 3 values, so that's again 6. And the fourth process would get the product of all 4 values, which is going to be 24. Okay, and the operation that you can use, right? You can use any of the reduce operations. So you can use sum, product, max, min, all of these operations. Okay, yeah, right. And so so every process needs to have a buffer containing the data that it's going to use in the scan operation. Okay, and it also has to have a buffer to receive all this information. Okay, so in this example over here, every process just has 1 data value. Okay, so therefore this count here is going to be 1, and the send buffer and receive buffers are only going to be have 1 value in them. Okay, but you could also send or receive a vector of values. Okay, so in that case, you would have a larger count, and then each one of these things, right, would be a vector of values. Okay, now when you do this scan operation, you're often doing the sum operation, and so in that case, this operation is also called prefix sum. Okay, so the reason it's called prefix sum is basically because you're taking a prefix of these processes and you're adding them, right? Like, so for example, this the third process here, he's taking a length 3 prefix of all of these values and he's adding them, right? This process over here, right, he's taking a length 2 prefix and he's adding them. Okay, so this is why it's called prefix sum. Okay. And this is actually, this scan or prefix sum operation, this is actually a very, very widely used operation. Okay, so we're going to see a lot more usage of this operation later. Okay, so it's kind of surprising how useful this this operation is. Okay, so we're going to see this a lot more later on. Okay, next we have the gather operation. So the gather operation is it's basically, imagine that every process has a piece of data, okay? And now we want to gather all of this data onto one particular process, the target process, okay? So, so when you call gather, if you're the target process, then you're collecting data from all of the other processes, okay? And if you're not the target, then you're sending data to the target, okay? Now, now, if you're the, let's see, if you're not the target, okay, then you're going to send a certain number of data items, okay? So that's what the send count is. So imagine that you're sending 2 items, okay? Then your send buffer would have 2 items of a certain data type, okay? Now, the difference is that the receive process, right, he's going to receive 2 items from each other process. So if there are, let's say, 8 other processes, right, then this receive process would actually get 16 values, okay? So basically, in general, if we have a communicator with k processes in it, right? So suppose that this COM has k processes, okay? And if each of these processes has a send buffer of size t, right? Then the target will need to receive k times t items. Okay, so therefore you need to the target needs to allocate a receive buffer of size k times t. Okay, now there's a very similar operation to gather, which is all gather. Okay, so this simply means that every process is going to do a gather. Okay, so when the first process does a gather, right, he gets the data from all the other processes, and then every process does that. So that's all gather. Okay, so the next operation is scatter. Okay, so scatter. Let's see. Yeah, so scatter is basically the reverse of gather. Okay, so gather is everybody has let's say k items, and I'm going to collect all of these items and end up with k times t items. Okay, scatter is the opposite. Here I start out with k times t items, right, where k is the number of other processes, and I send t items to every other process. Okay, so in fact, I have an array of data like this, right, and I'm going to send t items. I'm going to send the first t items to the first process, the next t items to the next process, and so on. Okay, so the interface for scatter is like this. Okay, so I have this send buffer over here, right, and let's see. So send buffer sends at I receive count. Okay, right, and then every process is going to receive count number of items from me. Okay, so suppose we have, let's say, k equals, let's say we have 8 processes, right? And then suppose my send count, or sorry, my receive count, right? Let's say that this is equal to 2. Okay, so every process is going to receive 2 values from me. Okay, so that means that my send count, right? I have to be sending out 2 times 8, which is 16 values. Okay, so my send buffer is going to have 16 values, right? And all of the other processes are going to have a receive buffer of size 2. Okay, so now the scatter is going to, the data is coming out of a source, right? And then all of the non-source processes will be receiving, and the source will be sending. Okay, now when you do a scatter operation, all of the non-source processes will receive the same number of items. Okay, so if there are 8 processes, every one of them is going to receive 2 items from me. Okay, but what if I want to send different numbers of values to different processes? Okay, so maybe you know, let's pick a smaller number here. Let's say that k equals 4. Okay, now what if I want to send something like, let's say for the first process, right, I want to send him 3 values. For the next process, I want to send him 1 value. And then I want to send the next process 2 values, and then maybe 4 values over here. Okay. In order to do that, I'm going to use this operation called MPI scatter v. Okay. So the scatter v operation lets me specify how many values I send to each other process. Okay. Now, when I do the scatter v, I'm going to have let's see. I'm going to have this vector over here, okay? And this vector is specifying how many values I'm sending to each other process. Okay, so basically this vector, I'm just going to write this 3, 1, 2, 4. I'm going to place this in a vector, right? And this tells me how many values I'm sending to the other processes. Okay, now in total, I am sending, what is this, 4 plus 2 plus 4, so it's going to be 10 values, okay? So therefore, my send buffer, right, has to have 10 values in it, okay? Now, there's this other parameter, displacements, okay? So this displacement tells me where the data is actually located in my send buffer, okay? So imagine that I'm sending data over here, right? So I'm going to send 10 pieces of data, right? So we have, let me just draw this out. We have 2, oops. We have 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's a bit too long, I guess. right? So is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. All right. So this displacement, right? It's going to tell me. So what I want to do is I want to send. Let's see. How do I represent this? Okay. I want to send 3 data items to the first process, right? And I want to send 1 item to the next process. Let me move this a bit. 3, 1, 2, 4, right? 1, 2, 4, right? I want to send 2 items to the next process, and then 4 to the final process. Okay, so the displacement is just telling me where the data I'm sending starts. Okay, so the data I'm sending to the first process starts at index 0 over here, right? The data I'm sending to the second process starts at index 3, right? Let me sort of clear this up a little bit. Okay, the data I'm sending to the second process starts at index 3, right? The data I'm sending to the third process starts at index 4, right? And the data I'm sending to the final process starts at index 6. Okay. All right. So in fact, how do I compute these indices? Okay. Well, the way to compute them is that the first index is always going to be 0 because I'm going to start at the beginning of my this is my send buffer over here, right? I'm going to start at the beginning of that, right? The next displacement is just going to be I'm going to take this vector of how many values I'm sending, right? And I'm going to do a prefix sum on this. Okay, so actually it's an exclusive prefix sum. Okay, so what that means is that the next value is just going to be the this value 3 over here, right? The next value after that is going to be the sum of these 2 values, right? Because I'm sending 3 values to the first guy and then 1 value to the next one. So the next displacement is 3 plus 1. And then the next and then the displacement after that is going to be the sum of the first 3 values. Okay, so that's going to be 3 plus 1 plus 2 is 6. Okay. Right, so this is how you compute these displacements over here. Okay, so in fact, we've already seen a use of prefix sum. Right, so I mentioned that prefix sum is useful, and already even just to do the scatter v operation, we would want to use a prefix sum. Okay, of course, we would compute this prefix sum locally, right? It would be the source node itself, which is doing a prefix sum on its send counts. Right, we're not going to do, unless you have a very, very large number of values that you're sending out. Right, we're not going to try to compute the prefix sum in parallel. We're just going to compute it by ourselves. Okay, the source. All right, and then when you're doing the scatter v, for all of the receiving processes, right? So all of the non-source processes, right? So since they're receiving values, then they don't really care about the first 4 arguments, right? Because those are just about how to send the values, and that's only relevant to the source process. Okay, so that's scatter v. Next, we have this all-to-all operation. Okay, so all-to-all, remember, this is basically every node is doing a scatter. You can think of it that way. Okay, so for example, this process 0 over here, right? If it does a scatter, right, then it's going to take this row of values and it's going to distribute them along all of the processes, right? So it's going to take this row and convert it to basically a column in this sort of matrix representation that we have. Okay, and process 1 is going to take its row of values, right, and then distribute them along the column of processes. Okay. Yeah. So that is how all-to-all works. The arguments are that we need to have a send buffer, right? So the send buffer would be all of these values over here, right? That's our send buffer, right? We need to say how many values we're sending and what type we're sending, right? And then also, since the processes are all going to be receiving data, right? Then we also need a receive buffer over here. Okay, we need to know how many values we're receiving. Okay, so that's all to all. The next operation is going to be MPI all to all v. Okay, so all to all v is so just as with scatter, you could try to send different numbers of values to different processes. Right, so with scatter, right, you can send different numbers of values to different processes. With all-to-all v, it's again like a scatter for each process, and you're sending different numbers of values to different processes, right? With the all-to-all, everybody sends the same number of values to each other process. Okay, with the all-to-all V, right, I can have this displacement vector, this vector of send counts, and this specifies how many values I want to scatter to each other process. Okay, and this thing over here, the displacement, right, so this is again one of these vectors that keeps track of where the data is starting in the vector that I'm sending to other processes. Okay, and again, to compute that, you can be using this prefix sum operation. Okay, so next, let's talk about the barrier operation. Okay, so the barrier operation is a way to synchronize all of the processes in a communicator. Okay, and what I mean by synchronize is that the barrier is going to make sure that all of the processes encounter this barrier before they do any operations past the barrier. Okay, so if you imagine that we have this MPI program, right? So we have some code over here, and then at some point we're going to call the MPI barrier operation, right? And then after that we have some more code. Okay, so if you put a barrier, then this means that all of the processes in your communicator, right, they're all executing this code, right? So they're all going to wait until all of the processes in the communicator hit this line in the code before they do anything past that line of code. Okay, so here's like a visual representation. So suppose that we have this barrier at some line of code. Okay, now maybe process 0 is the fastest process, so it's the first to reach the barrier. Okay, and then after that, processes 1 and 3 reach the barrier, right? And then process 2 reaches the barrier. Okay, so when they reach the barrier, these processes are going to wait at the barrier. Okay, they're not going to do any code that goes past the barrier, right? They're going to wait at this barrier operation until all of the processes have hit the barrier. Okay, and then after that, they're allowed to go past the barrier, and they're allowed to do these operations after the barrier. Okay, so this is a way for all of the processes to synchronize with each other. Now, when you use a barrier operation, you have to be careful because you have to make sure that all of the threads will eventually hit the barrier. Okay, so for example, suppose you have suppose that thread 2 here, right? It hasn't hit the barrier yet, and suppose somehow it crashed. Okay, so in that case, it will never hit the barrier, right? So so this process 2 crashed, so it doesn't exist over here. Okay, then these other processes 0, 1, and 3 are going to be waiting at the barrier forever, right? Because these guys can only go on when everybody reaches a barrier, but because process 2 crashed, it's never going to reach the barrier. Okay, so all of these other processes are blocked forever. Okay, so if you use a barrier, you need to be careful about these situations where some processes may never reach the barrier, right? That would be very bad. Okay, another thing is that you can actually use multiple barriers. Okay, so so the way you can do that is suppose let's draw this timeline over here, right? Suppose you have a barrier over here, okay? So that means that you're going to wait until all of the processes hit this barrier before you go on past the barrier, okay? Now, after the first barrier, you could have another barrier, okay? So what that would mean is that all of the processes would now have to, so I'm having trouble erasing this, okay, all right. So all of the processes would have to hit the second barrier before they can go past the second barrier. Okay, so therefore, the processes are going to be sort of operating in phases. Okay, so oops. So what I mean by that is all of the processes will be doing this part of the code first. Okay, and then they won't be able to do anything in the next. They won't be able to do the next chunk of code until everybody has done this chunk of code. Okay, and once everybody has done the first chunk of code, the next all the processes are going to do the next chunk of code. But none of them can do the third chunk of code until all of them have finished the second chunk of code. Okay, so you can think of the barriers as breaking the code into these phases, right? And the phases have to be done in the same order by all of the processes. Okay, so that's basically all of the collective operations that I want to talk about. And now I want to show you how we can make use of these operations to actually solve a problem. Okay, so the problem we're going to solve is something involving matrices. So I'm first going to talk about how matrices are stored when you do parallel computing. Okay, so I'm going to assume here that these are dense matrices. Okay, and that just means that when you have a matrix, basically most of the values are non-zero if you have a dense matrix. Okay. The other type of matrix is a sparse matrix where many of the values are zeros. Okay. If many of the values are zeros, then you don't actually have to store all of those zero values. So when you have a sparse matrix, you have lots of different special storage formats for these sparse matrices, which can make the operation more efficient, right? It can use less space and you can compute faster. But if you have a dense matrix, then basically you have to just store all of the values, right? Because almost all the values are non-zeros. Okay, so anyways, now we're going to do some linear algebra on these dense matrices. Okay, and in fact, linear algebra is one of the main applications for parallel computing, right? Because many problems can be solved by linear algebra, and also linear algebra is very suited to parallel computing. Okay, so it's one of the big applications. Okay, so now if we're working with a matrix in a distributed setting, then we don't want to have each process store the entire matrix because the matrix can be quite large, right? So instead, we want to break up the matrix and then divide it among the processes. Okay, so there are different ways of dividing the matrix. Two simple ways are to either break up the matrix in terms of its rows or its columns. Okay, so that's going to be called row or column striping. Okay, so for example, if we break up the, sorry, let me go back. So if we break up the matrix in terms of its columns, right, so then we have a column-wise block stripping or striping. I think it's called striping, not stripping. I guess you could call it stripping also. Yeah, so we have these columns, which are these strips, okay, or stripes, whichever one. And then you can also do the row-wise block stripping, where you break the thing into columns. Into rows. Okay, and you assign different sets of rows to different processes. Okay, now I want to mention that. Okay, so each process is going to get a subset of either the rows or columns. Okay, but we still have to organize the data from the subset in some manner. Right. So, for example, in the row striping, right, this process P0, it's got the first 4 rows, but how are these rows represented in P0's memory? So they're usually represented in row major format. Okay, especially if we're working with C, right? So C stores matrices in row major format, and what that means is that we're going to store the first row of data, right, and then followed by the second row, right, followed by the third row, and so on. Okay, so this is why it's called row major format. Okay, now if we're using this column striping, right, we're still going to store things in row major format. Okay, so what's going to happen is we're going to store these first 4 values. So P0 is going to store the first 4 values, right, followed by the next 4 values, and in this fashion. Okay, so you have this sort of zigzag pattern for how you store the values. Okay, so that's for storing the matrix. Now, what is the problem that we're trying to solve in parallel? So the problem we're trying to solve is we want to take a matrix and multiply it by a vector. Okay, and just to make the problem a bit more complicated, we're going to assume that the matrix is actually stored in the column-wise format. Okay, so for example here, let's say we have 6 processes. Okay, so then each process has some subset of the columns of the matrix, okay, of the matrix A. And then there's another vector x that we're given, and our goal is to compute the product of A and x. Okay, so call that y. Okay, so now let's say that A is an m by m matrix, okay, and then x is going to be an m by 1 vector. Okay, and let's say that you have p processes. Okay, so in that case, we are going to have n rows over here, and then each process is going to have n divided by p columns of the matrix. Okay. Now we're also going to assume that the each process has n divided by p values of the vector. Okay, so each process doesn't have the entire vector. It's only got a certain part of the vector, right? Okay, so now given this format, how do we do the matrix vector multiplication? Okay, well, what we need to do is so here there are many. The first process has many rows, right? Each of these rows has n divided by p values. Okay, and the first process also has n divided by p values of x. Okay, so then what we want to do is we want to take these n divided by p values from the first row and then multiply by the n divided by p values from x, right? We want to do the dot product of that. Okay, and the dot product will, so the dot product just means that, you know, if you, we're going to take a bunch of values. So if you want to do the dot product of like 1, 2, 3 with, let's say, I don't know, 3, 2, 1, let's say, right? Okay, then you're just going to do these, you're going to do like 1 times 3, right? Plus 2 times 2 plus 3 times 1. Okay, you're just going to match up these values one by one. You're going to multiply them and then you add them up. Okay, so to compute, yeah, so this blue process, the first process, is going to do the dot product of the first row with these values of x. Okay, so that's going to end up producing a single value. Okay, that's going to combine everything into like a single value. Let's just sort of draw it as, I don't know, like an x over here. Okay, or let me not call it x because I've already got this x over here. Let me call this v. Okay, or let's take v1. Okay. And then this first process is going to take the second row, right? And then multiply it again. It's going to take this second row over here. And again, it's going to compute the dot product with these with this part of x that it's got. Okay. And that's going to produce another value, v2. Okay. Right. And then it's going to take the third row and dot product with these values of x. And that's going to produce v3 and so on. Okay. Right. So basically in the end, right, we're going to end up, the first process is going to end up with n different values. Okay, now the second process is going to do the same thing. Okay, it's going to take its first row of n divided by p values, and it's going to multiply it by these green values of x over here. Okay, and that's going to produce a value. So let's call that thing w. Okay, w1. Okay, and then it's going to take the second row and again dot product with these x values, right? And let's say that this is going to produce a value w2 and then w3 and then so on, and it's eventually going to end up with n values. Okay, now the third process does the same thing. So it's going to take its first row multiplied by these yellow values over here, and let's say that it gets a value of u1, and then it also gets u2, u3, and then so on. Okay, and then everybody basically does this. Okay, so now after all of the processes have done this, right? I'm sorry. Let me keep this around. Okay. You know what? Let me erase this. Okay. So what I want to say now is that every process after it does this, right? Then we're going to get since we have p processes, we're going to end up with p of these values. Okay. Now, what we want to do is, I think I'm going to have to switch to a different color here that is not red. So let's just go with blue over here. Okay, right. So what we want to do are we want to compute these values, right? Like y1, y2, and then so on up to yn. Okay. So what is y1? Okay. So y1 is actually equal to this entire row, right? Multiplied by this entire vector x. Okay, now how do we get y1? Well, what we can do is, now if you look at these individual values, the v1, the w1, and the u1, okay, so each of these is part of this row, right? So each of these is part of the overall value of y1. Okay, so then what we want to do is we actually want to add up all of these values over here. The v1 plus the w1 plus the u1 plus all of the first row values from all the processes. Okay, and when you add them up, then that sum equals y1. Okay, now what about y2? Well, y2 is we're going to take all of these second row values, right? The v2, the w2, the u2, and so on, all of the second row values from all of the different processes, and then you're going to add them up, and then that gets you y2, right? And same for y3, you take all the third row values, right? The v3, w3, and so on, and that the sum of those is y3. Okay, so this is the algorithm, right? So the algorithm is let's see. Okay, so the algorithm is that first, all of the processes are going to do dot products, right, of their rows with the portion of x that they have. Okay, that's going to produce all of these v1, v2, v3 values, or w1, w2, and so on. Okay, and then after that, we need to add up all of these v1, w1, u1, or v2, w2, u2s. Okay, now this addition process, okay, we actually have a very good tool in MPI for doing this, and this is the reduce function. Okay, so if you think back to, so I guess I can actually go back a few slides. So we have this function called reduce, right? And this reduce function is perfectly made to do this, because the reduce is going to take values from all of the different processes and just add them up. Okay, and that's exactly what we want to do when we compute this this matrix vector product here. Okay, we want to do a reduce on all of the first row values, and then we also do a reduce on all of the second row values, the third row values, and so on. Okay, so reduce is perfect for that. Okay, and then next, so when you do this reduce, right, all of the values get accumulated onto one particular process. Okay, so because you have to reduce onto one particular process. Okay, so that process is going to end up, so whoever we reduce onto, that process is going to end up with this entire vector y. Okay, however, in the end, we don't want just one process to have this entire solution vector, right? We want all of the processes to have portions of y. Okay, so then what we're going to do is after we reduce onto this the single process, then that process is next going to chop up y, right? So it has all of y, but it's going to break it into these different parts, and then it's going to scatter these different parts to the different processes. Okay, so for example, this part goes to process 0, this part goes to process 1, process 2, and so on. Okay, so it's going to use a scatter operation to do that. Okay, so now let's try to put all of this together into some code. Okay, so here we have the program for doing this. Right, so what is happening is, so now remember that the first thing that you need to do is each process is going to compute these dot products, right? It's going to take its all of its rows, oops, right? And then these partial rows, and then dot product with this partial part of with this part of x that it's got. Okay, so that's what's happening in this part of the code, right? It's computing all of these. It's computing n of these partial dot products. Okay, so the next thing is that we have to take all of these partial dot products and add them together, right? So we said that that was the reduce operation. Okay, and we're going to reduce all of these values onto let's say process 0. Okay, we can pick any process. Let's pick process 0. Okay, so the values that we reduce are these partial values, the partial y's, right? And then we are going to we're going to collect all of these values onto process 0, and he's going to store it in fy. Okay. And then the final thing to do is that now process 0 has all of the y values, right? And he wants to distribute different portions of these y values to different processes. So therefore, the process 0, he's going to do a scatter operation of these y values, right? And he's going to give n local values to each process. Okay, what is n local? N local is defined as the total number of values defined by the number of processes, right? So if you have like 100 values and 5 processes, right? Every process should get 20 values. Okay, so n local would be 20. Okay, so you do the scatter operation from process 0, and now everybody gets their correct portion of y. Okay, yeah. So this is how you can do this linear algebra operation using these collective operations, right? The reduce and the scatter. Okay, now in the final part of this lecture, I'm going to talk about these other types of operations that you have in MPI, which are the data type operations and the operations on communicators. Okay, so let's first talk about how would you define new data types in MPI, right? So MPI comes with like basic data types like ints and doubles and floats and so on, right? But if you want more, if you want to define like, let's say, a structure of these, okay, you can actually do that in MPI. So the way we do, so there are four main types of these derived data structures in MPI. Okay, so they're called contiguous, vector, indexed, and struct. Okay, so in order to define one of these types, so you're going to define a data type, right? So I'll show you how you can create the definition of these various data types, and then after you've created the defined the data type, you're going to commit the data type. Right, you're going to tell MPI that I want this kind of data type. Okay, so you're going to use MPI commit for that. Okay, some other operations you have are if you call this MPI type extent, right, you get the size of that data type, like how many bytes it uses. Okay, and then you can call MPI free to free this to free a variable of this data type. Okay, so now let's look at how to create these different data types, right? So we have four types of contiguous, vector, index, and struct, right? So contiguous is pretty simple. It's just taking, so you start out with some basic data type, let's say floats, okay? Now suppose you want to define a new data type which has 4 floats, okay? So then we're just going to place the 4 floats contiguous to each other. So that means that we put one right after the other, okay? And then you can define a new data type. Let's call that float 4, right? And so to do this, you just set O type to be float or MPI float, right? And then you set count to be 4 because you want 4 of them. And then the new type, you can define, just give a name to it. Let's say float 4. Okay, so that's how you use MPI contiguous. Now these other types, okay, so they're actually kind of more complicated. So instead of reading through this, this function definition for you, right? Let me just show you examples of how to do this. Okay, so the MPI vector data type. Okay, so basically what's happening over here is that usually the way you use this vector data type is that if you have a matrix, okay, then maybe you want to select certain parts of this matrix. So for example, you might want a sub-column of this matrix, okay, or sorry, just a column of the matrix, or maybe you want a row out of this matrix, okay. So maybe you want to put, so here let's say that you want this entire column of values, you want to put all of those into a struct, okay. So you want a struct corresponding to a column of a matrix, okay, and easy way to do that would be using this MPI type vector thing. Okay, so how do you use this? So here, what you need to say is that when you use this, so let me go to red again. Yeah, so so when you use this MPI type vector, you're going to say that I'm going to make a vector of size. So here I want a column of size 4, right? So my size here is going to be 4. Right, so here size is defined, right? What are these other arguments? Oh, okay, right. So the next argument is this block length argument, okay? And so what this is saying is now from this matrix, right? I want to take so here my block length is 1, so this means that I want to take one value at a time from the matrix. Okay, if my block length were 2, I would be taking 2 consecutive values from the matrix. Okay, but here my block length is 1. Okay, and then the next argument over here is stride. Okay, so stride means that, so here my stride is 4. So this means that I want to take every 4th value. Okay, so I'm taking this value, and then I skip 3 spaces, and I take the next 4th value. Okay. So remember that this matrix is stored in row major format, okay, inside in memory, okay. So if I take this value, the 2, right, and then I skip 3 values, my stride is 4, so I'm going to skip 3 values and take the next 4th value, okay. So since every row here has 4 values, then that's going to take me to the to the same column, but in the next row, the 6, okay. And then again, I'm going to skip 3 values and take the next 4th value. So again, this is going to be in the same column, but the next row. Okay, so so this 4 tells me that every time I take a value, the next value I want is going to be, I need to skip ahead by 4 spaces. Okay, and yeah. Okay, and the values that I have, all of these values are floats. Okay, because all of these values in the matrix here are floats. Okay, and then lastly, I'm going to give a name to this data type that I defined, right? So I'm trying to take a column of values, so therefore I'm going to name this column type. Okay, so this MPI type vector here is going to define one of these column types, and it says that, again, we have 4 different values in this column type, right? How do we get these values? Well, what we do is we start somewhere, okay? So, and then you're going to take 1 value from the starting location, right? And then you skip ahead for 4 floats, and then you take the next value, and then again you skip ahead 4 floats, and you just keep doing that, and you do that a total of 4 times because we have a size of 4. Okay, so this defines the MPI column type, and then we're going to commit this type. Okay, so this is going to tell MPI that I want to have this type. Okay, now let's see how we actually use this column type. So we're going to have a program where initially the rank 0 process, he's going to have this entire matrix. Okay. And we want the rank 0 process to send the different columns to the other processes. So he's going to send, he's going to send the first column, okay, to the first process. He's going to send the second column to the second process, right, third to the third process, and so on. Okay, so this is what we want to achieve with this program. Okay, so how do we do that? Well, since we define this column type, right, the only thing we need to specify is this column type needs to start at a location. Okay, so if we start at this value, then we're going to take this column. Okay, if we start at this value, then we're going to take this column, right? So what we do over here is that since you want to send the ith column to the ith process, right, then the starting point for the ith process is going to be the, in the first row, we're going to take the ith value. Okay, so this is A0I, right? And then from there, we're going to build a column type. Okay, so for example, for the first process, right, we're going to start with A00 and build a column type, and that's the first column, right? For the second process, you're going to start with a 2 and build a column, and so on. Okay, and then after that, you're going to use MPI send to send this entire column of 4 values, okay, to the other processes. Okay, and then if my rank is not 0, right, then I'm going to be receiving values from the rank 0 process. Okay, so and when I receive something, I'm going to say that I'm going to receive 4 floats. Okay, because each column has 4 floats. Okay, and then after that, I'm just going to print out my rank. Each process prints out its rank and the values it receives. Okay, so now if you run this program, right, what's going to happen is the first process is going to receive the first column of values, right, so 1, 5, 9, and 13, and it's going to print those out, right. The second process is going to receive the second column, right, 2, 6, 10, and 14, prints that out, and so on. Okay, so again, the vector data type lets you sort of build these either columns or other other collections of these strided data in a very simple way. Okay, so here the stride is 4, right? So 4 and then 4 and then 4. Okay, so that is the vector data type. Now let's talk about let's see. So we also have this index data type. This is actually quite similar to vector except for here, the stride for the vector, the stride is the same for every value in the vector, right? Whereas for the indexed, you could have different strides, okay, for different values, okay? And so those different strides are given by this offset. Okay, so I'm not going to talk too much about that because it's similar to the vector type. I'm going to show you how to use the final data type, which is struct. Okay, so struct lets you build a general structure. Okay, so you know that we have these structs in C, which is just a general data type, right? And so for MPI, if you want a struct, then you're going to create them using this this type struct. Okay. So for the example here, the struct that we're going to have is going to have six values in it. Okay. So for the first 4 values, they're going to be floats. And then we're going to have 2 more ints. Okay, so 4 floats and 2 ints. Okay, so we want to define such a data type, and we're going to call this data type a particle. Okay, because this is supposed to capture some information about a particle. Okay, so in order to define this, right, what we have to tell MPI is we have to tell it the type of each of these locations in the struct. Okay. So now, so the first part of the struct is going to be 4 floats. Okay, so we're going to say that the first part of the struct is going to be floats, right? The offset, which is like the starting location for the floats, is going to be 0, right? And we're going to have 4 of them. Okay, so next we want to have 2 ints, right? So then what we tell MPI is that the next set of items are going to be ints. Okay, so the first set of items, right, are going to be floats, and the next set of items are going to be ints, right? What is the starting point for these ints? Well, it's going to be 4 times the size of a float, right? Because we have 4 floats initially. Okay, so therefore it's going to be 4 times the extent, and extent is going to be the size of a float, right? So so here we call extent to get the size of a float. Okay. And then how many ints are we going to have? Well, we're going to have 2. Okay, so we're going to specify the 2 over here. Okay, so in our code, this is what we write. Okay, so the offsets for the floats are going to they're going to start at 0, right? We have these floats. We have 4 of them, right? And then next we're going to tell MPI about the ints. Right, so then we're going to say that the ints are going to start out at 4 times the size of a float, right? They're going to be MPI ints, and we have 2 of them. Okay, so now we've built this matrix, these 3 vectors, the offsets, the old types, and the block counts. Now we can call MPI type struct with these counts, the offsets, and the types, right? And that is going to create a new type, which we're going to call particle type. Okay, and after creating that, we're going to commit it. Okay, now the final thing is to use this type, and the way we're going to use it is we're going to create a bunch of particles, right? And then for each particle, we're going to initialize these floating point values and the integer values. Okay, so the way we initialize it is that for the we're going to create n elem is going to be 25 over here. Okay, 25. So we're going to create 25 particles, and for the ith particle, the x coordinate is going to be the I times 1, right? Y is going to be I times -1, and so on. Okay, so we're gonna initialize 25 of these guys, right? And then we're going to send these particles. Okay, these 25 particles, right? We're going to send them to I guess we're going to send them to all of the other processes. Okay, yeah. So every process is going to be receiving 25 of these particles. Okay, so every other process receives these 25 particles. And the final thing is we're going to have all of the processes print out the information for the 3rd particle that they receive. Okay, so yeah, so for the 3rd particle, they're going to receive all of these values are going to be I equals 3. So it's going to be 3 and then -3 and then 3 and then 0.25 and then this is going to be a 3 over here, and then 3 modulo 2 is going to be a 1. Okay, so every process is going to print out this array of values. Okay, all right. So right. So next, I want to move on to talking about communicators. Okay. So for communicators, you know, we start out, when you start your MPI program, you start out with this default communicator, the MPI com world. Okay, but you can build your own communicators. And so here, I'm going to show you an example of doing that, where we're going to take the MPI com world and we're actually going to break it into two parts. Okay, so suppose that our MPI com world actually has 8 processes. So now we're going to create 2 communicators, each with 4 processes. Okay, so we're going to take the first 4 processes from MPI com world, put them into one communicator, and then the other 4, we're going to put them into a different communicator. Okay, so the way we do that is that we're going to have this communicator. Where is it defined? Let's see. Okay, so the new group. This is what I'm looking for. Let's see. Oh, okay. Right, here we go. Okay, so for the new group. Okay, so this is a group of processes. Okay, so we're going to create 2 groups, right? So we're going to have 2 new groups. Okay, the first new group is going to have processes with ranks 0, 1, 2, 3 in the original communicator. And the other group is going to have processes with ranks 4, 5, 6, 7 from the original communicator. Okay, so what we're going to say is that each process, 0 up to 7, is going to compare its rank with this is going to be 4 over here. Okay, we have 8 processes divided by 2 is 4, right? And if it's less than 4, then it's going to use the first set of ranks, right? And it's going to get included into the new group. And otherwise, it's going to use the second set of ranks and get included into the new group. Okay, so this is going to split our processes into two groups based on the ranks. And then we're going to create a new communicator, right? This new communicator based on these groups of processes. Okay, and then each process is going to do an all reduce within its group. Okay, and the all reduce value is going to be based on either ranks 1 or ranks 2. Okay, so so if you're in the first group, then when you do the all reduce, and so here we're doing a sum all reduce, then we're going to be adding up 0, 1, 2, 3. Okay, so that's going to be 6, right? And if you're in the second group, then when you do the all reduce, you're going to be adding up these values, and so this is going to be it's going to be 22 over here. Okay, the sum of these 4 values. Okay, and then finally, you're going to print out your old rank and your new rank. Okay, and you're also going to print out this all reduce value that you have. Right, you're going to print out your receive buffer value. Okay, so what's going to happen is if you run this, you could get an output maybe like this. Okay, so here you see that you know, the processes 0, 1, 2, 3. Oops. If the processes with old ranks 0, 1, 2, 3, right, their new ranks are again 0, 1, 2, 3, right, and the value that they receive is the sum of 0, 1, 2, 3, so that's going to be 6. Okay, and these other processes, the processes 4, 5, 6, and 7, right? So since they go into a new communicator with only 4 processes, their new ranks are going to be 0, 1, 2, and 3. Okay, but the value that they receive was the sum of their old ranks, which is 22. Okay, so they're going to receive these 22 values. Okay, so this shows you how to create new communicators based on processes from previous communicators. Okay, right, so I'm going to do one more example with something called virtual topologies. Okay, so what this does is, so when you have a communicator of processes, you just think of these processes as a set. Okay, you don't think of them as being organized in any way. You There's no sort of topology associated with these processes. Okay, but sometimes you might want to take these processes and you might want to say that, well, these processes should actually be organized in a mesh topology, for example. Okay, or maybe some other type of topology, maybe a hypercube topology. Okay, and yeah, so the reason you want to do this is that so for example, this set of processes in the communicator, okay, maybe they communicate based on a mesh pattern. Okay, so you have a bunch of processes, right, and maybe their communication pattern is not just arbitrary, right? Like, for example, this process would never directly talk with this process, right? It would only talk with its neighbors. Okay, in that case, you want to in that case, you can actually tell MPI about the communication topology of your processes. And if you tell MPI about this topology, then what MPI can do is to try to map this process topology onto the actual physical processor topology. Okay, so remember that a few lectures ago, we talked about how to map the process topology onto processor topologies. Okay, so initially, if you just have a communicator, then MPI doesn't know anything about your process topology. Okay, so these virtual topologies are a way to inform MPI about your process topology. And once you inform MPI, then it can try its best to map these in a good way onto the actual physical processor topology. Okay, all right, so yeah, okay, and the way that we can do this is that there are two main types of topologies in MPI. Either these meshes, or so there's something very similar to mesh, which is the torus. So torus just means that you connect the first and last processes on each row. Okay, yeah, so those are the toruses, or you could have a graph topology. Okay, so those are the two main types. And to create those types of topologies in MPI, you have these, so to create these toruses, you use the MPI Cartesian create, okay, or cart create, okay? And then for the graph, it's more complicated, but you have this graph creation thing, okay? So I'm not gonna go through the graph creation process. It's kind of complicated, and if you're interested, you can look that up in the MPI documentation. So all I'm going to do is just show you an example of the of creating a mesh topology. Okay, so so the way this works is that suppose you have 16 processes. Okay, now you want to tell MPI that these processes are organized in a 4x4 mesh. Okay, and so the way you can do that is so we have 16 processes over here, right? So we're going to say that these are organized in a 4x4 mesh, right? And here you can use this MPI Cartesian create function, right? To say that we have a two-dimensional topology because it's a two-dimensional mesh, right? The dimensions of the mesh are 4x4, right? Over here we have 4x4, right? The period basically means that are these topologies, are they toruses or are they just lines? Okay, so if it's a torus, then the first node is connected to the last node. Okay, so here we do not have toruses in both the x and y directions, so we set these periods to be 0 here to say that this is not periodic, right? And then yeah, and then you call this MPI cart create, and this is going to create, this is going to place your 16 processes into a 4x4 two-dimensional mesh. Okay, now we want to check that this mesh works correctly, and so what we're going to do here is that we're actually going to call these, we're first of all going to get our coordinate, our coordinate within this mesh. Okay, so the coordinate is just like an ij coordinate, right? Like which row and which column you're in. Okay, so it's two values. Okay, and then after that, we're going to call. We want to find out for each process what is the process above and below that process. Okay, so for example, for process 5, the process above it, right? The next process is going to be 9, right? The process, the down process is 9, and the up process is 1. Okay. And you also want to find out which processes are to the left and the right. And so this is, so the left process is 4 and the right one is 6, right? So to do this, you can use this MPI Cartesian shift operation, okay? So this Cartesian shift, so first of all, it needs a communicator. So we have our Cartesian communicator over here, right? So this first argument the second argument is the dimension that we're talking about. Okay, so 0 means the x dimension, 1 means the y dimension. 0 means the y dimension, apparently. Okay, so 0 means the y dimension, and this 1 here is the x dimension, right? So this 1 is saying that, you know, I want to go I want to take one hop either from, either towards somebody or from somebody. Okay, so if I take one hop towards somebody, right, in the y direction, then, for example, if I'm 5 over here, if I take one hop towards somebody, I'm going to get to 9. Okay, so the guy, let's see, so is this correct? No, I guess if I take one hop towards somebody, I'm going to get to 1. Okay, so I went in the wrong direction. Okay, so so this is my up neighbor. Okay, and then my down neighbor, how do I find who's below me? Well, here, this final argument over here is who can take one hop and get to me? Okay, so I'm node 5 over here. So who can take one hop and end up at 5? Well, that would be 9, right? So 9 can take one hop and end up at 5. Okay, so that's my down neighbor, right? Okay, and to get the left and the right neighbors, again, I have this one hop thing over here. And so the first one is saying that, I think I got these reversed. I guess it doesn't matter that much. I mean, you can look up the details, but I think the first one, you know, the left one is, is going to be who can take one hop and get to 5. Okay, so that would be 4. Okay, so 4 is my left neighbor, right? And then my right neighbor is who would I get to if I took one hop, right? So I'm 5. If I take one hop, I get to 6. Okay, so and every process does all of this, right? So then every process can find out its up, down, left, and right neighbors. Okay, and the final thing is for the processes to print this out. Okay, so yeah. Okay, so if you run this program, then basically what's going to happen is all the processes are going to print out all their neighbors and their coordinates. Okay, so for example, if your process 0, right, your coordinate is going to be 0, 0 over here, and your neighbors so are going to be, well, you have a down neighbor 4, right, and then you have a right neighbor 1, right, but you don't have a left neighbor and you don't have an up neighbor. Okay, so in this program, when you don't have one of these, you know, the values here are going to be -1. Okay, now if you're some other process, let's say if you're process 10. Okay, so if you're process 10 over here, right, so then your coordinates are going to be 2, 2, right, and then your up, down, left, right neighbors are going to be 6 up, 14 down, and then 9, and then 11. Okay, so this is how you use these topology creation operators. Okay, all right, so we're almost done here. So the final thing I want to say about MPI is that so all of the functions I've described exist in MPI 1. Okay, and MPI 1 is actually very powerful, and you can use that to write many programs. Okay, however, there are newer versions of MPI, like there's MPI 2 and 3. And so I'm not going to talk too much about them, but basically what MPI 2 did was that it allows for dynamic process creation. Okay, so remember that initially I said that MPI, as soon as you start the program, you have to start all of your processes. Okay, MPI actually allows you to start new processes during the execution of your program. Okay, it also, MPI lets you do collectives across different communicators. In MPI 1, I think you can only do collectives within each communicator. Okay, so MPI 2 also improved input-output. Okay, so if you need to read from disk, you can now do that in parallel. Okay, and MPI 2 added this thing called one-sided communication. Okay, so MPI 1 is basically two-sided communication, because if I want to get a value from somebody, right? Or sorry, let's say I want to send a value to somebody. Okay, then I'm going to do a send, and the other process needs to do a receive. Okay, so we need to coordinate with each other. It's a two-sided process. Okay, but for MPI 2, you can actually do one-sided communication. Okay, meaning that I can just try to send you a value, and you don't need to be expecting that value. Okay, you can just receive the value, even though you don't need to know a priori that I'm planning to send you this value. Okay. And then MPI 3 sort of improved on MPI 2. So now it made the collective operations non-blocking. It also allows multi-threading, and then it improved some of the one-sided communications. Okay, so this is all I have to say about MPI. And the next time, we're going to look at how to actually implement these collective operations. Right? So I mentioned that one simple way to implement them would just be as a bunch of individual point-to-point operations. But this is not an efficient way to implement these things. So next time, we're going to see how to implement these collectives in a more parallel and in a more efficient manner. Okay, so see you guys next time.